right, so here we are going to begin learning about proofs. Before we get into geometric proofs, we're going to talk about some algebraic proofs which you've actually seen before, and they all start with these properties that we've seen. So these properties, which actually we began our first lesson by defining some of these, we're going to use them to justify any algebraic operations that we do when we solve an equation. And there's other ways that you can use them, but that's the example that we're going to use here. So you can see actually what's happening here in this very simple equation, 3x minus 9 equals 0. We want to prove that x equals 3. So we have the given statement. This is how we are going to start every single proof, starting with whatever is given to us, because that has to be the foundation of our proof. And then from there, using a postulate, property, definition, or theorem to justify whatever we did in the statements on the left side. So we can see going from that step 1, which is given to us, to step 2, all we really did was cancel out this minus 9 by adding on both sides. So here, it's called the addition postulate. You can call it that, or you can call it the addition property of equality, or if you even want to abbreviate that, you can call that APO, addition property of equality. Either of those two are really okay. The addition postulate, I would probably say the addition property of equality, but really, that's up to you. But that justifies this step of adding 9 on both sides, going from step 1 to step 2, and then step 2 to step 3, we are dividing on both sides. So they're calling it division property or division postulate. I would call that division property of equality, or if you want to abbreviate that as DPO, that's fine. So you really have to have these algebraic properties memorized just so that you know how to use them. These are all going to be tools that you can use to justify solving an equation, and then later we're going to get into our geometric postulates, definitions, and theorems and use those as tools to justify geometric proofs. All right, so just so you can get a feel for what these two-column proofs look like, and that's what this is, a two-column proof, having a statement on the left side and then a reason to justify that statement on the right side. We are going to try to prove that x equals 25 in that equation. So the first thing I'm going to do every single time is write out my given statement. For solving an equation like this, it's really easy because it will literally just be copying that down and saying that that was given to me. For geometric proofs, sometimes you're given more than one piece of information, so you have to kind of decide where you're going to start. My first step here is going to be distribute. It doesn't have to be, but I'm going to distribute. And you could say the full thing, the distributive property, or you can punctuate it. A lot of these, you don't want to have to write out the entire thing when you're just laying out the two-column proof. So you can abbreviate it. As long as you're clear in your reasoning, you're allowed to abbreviate it like that. So I'm going to distribute here. And in general, actually, you don't want to do this part. You don't want to actually show the operations happening. You just want to show the result of that. So I'd get 5x plus 20 equals 6x minus 5. And now you have some options here. So there's no one right way to do this. I'm going to use the subtraction property of equality by subtracting 20x from both sides. That leaves me with 5x equals 6x minus 25. And then I'm going to actually use the subtraction property of equality again. I'm going to subtract 6x from both sides, giving me negative 1x equals negative 25. And my last step will be the division property of equality. I'm dividing by negative 1 and dividing by negative 1. That gives me that x is 25. So I have proven the desired statement. And I've justified each of those steps with a property that I know is true for equality. All right, now I'm going to do one more of these. I have this given statement of 5 minus 2 times 3 minus x equals 4x plus 10. That is my given statement. And again, there's no one right way to start out. I could subtract that 5 from both sides, but I like to distribute first. So I'm going to take that negative 2 and distribute it into both terms on the inside of that parentheses. So negative 6 plus 2x equals 4x plus 10. That was using the distributive property. Then I'm going to combine my terms on the left side. When you do this, you can call this simplifying. So for right now, I'm comfortable giving you this a little bit skipping of logic. Anytime you're using commutative, associative, identity, or inverse, or combining like terms, I'm okay with you just calling that simplifying for our purposes. So we're going to just subtract those and get -1 plus 2x. And now from here, it's going to look very similar to the previous one. I'm going to cancel out this -1. I'm going to add 1 on both sides. So I'm going to do +1 there to cancel that out. It gives me 2x equals 4x plus 11. And then I'm going to use the subtraction property of equality to cancel out this 4x. It gives me -2x equals 11. And my last step is to divide away this -2. So I get x equals 11 over -2, which is the exact same thing as that. And that's exactly what I wanted to prove. So x does equal 11 over -2. So this logic of having a statement and justifying it with a reason that you know to be true is really what we're going to take from this and use in geometry.